All right, number 2, you guys can already see it. Initial and then terminal. Initial and then terminal. Number 8, multiplication and addition. Number 14, you can see all the different pieces. There's your component form, and there's your magnitude. They simplified root 20. By seeing 20 as 4 times 5. Number 22 is coming. There's component form. Remember, terminal minus initial. There's component form, and there's magnitude for number 22. Couple more seconds. We all on the same page? Number 42. This was one of those take a current vector and find his unit vector. So to do that, you had to find his current magnitude by using the square root of a squared plus b squared formula, and then divide both of the components by that number. So that's your final answer. They said just double check by plugging in. Yeah, you could do the linear combination. So 5/13 I vector plus, or I should say minus 12/13 j vector. Number 54. I'll keep that one up for a couple more seconds. 54. I think you were just doing, once again, component form, and then you were making that linear combination form. Check your notation. You put little arrows above all of our bold letters. Remember your vectors, they need to have little vector arrows above, not just letters. J is a vector, I is a vector, U is a vector, okay? You got it okay? Number 72. This was one where you had to plug and chug. This is the one, wrong class. This is the one where you were using magnitude, cosine angle, magnitude, sine angle. So you could have gone ahead and plugged in the magnitude with cosine 90, magnitude sine 90, or some of you might have just graphed it and said, hey, you know what? I know that point. It's the y value with an x value of 0. So you could have kind of cheated on that one. Or you could have just plugged into the formula and gotten the same thing. Final answer, 0 for root 3. 96 was a plug and chug, which would have been ridiculously hard if you had not remembered in notes that we had done a word problem very similar to that problem. Because I think, wasn't this an incline one, guys? I'm trying to get up the word problem. In the incline one, the math looks really easy. What's hard is some of you were not paying attention to the picture. Whenever you have an object on an incline, remember I told you, one of these 3 types of, where's the other one? Ah, there he is. One of these 3 types of word problems is going to be on the test. And this one in particular, the math is easy, but the setup is hard. I wouldn't give you this huge picture on the test if I gave you this one. I might just put somebody on a hill and say solve. You would need to know this triangle, hence why we highlighted it, we labeled it. So in homework, they gave you the force required to hold it or pull it, and then the work. No, weight. Isn't that the weight?
Work.
It is the weight? What's F stand for?
Wait. Force. Wait. It's the weight.
Okay, I think it's the weight. Right?
Yes, it is.
Okay. So they wanted us to find each of the different components, and the only way you would know that is if you knew, hey, I have an angle, I have an opposite, and I have a hypotenuse, so you knew to use sine. If you didn't know to use sine, you'd be in some trouble. Oh my goodness, I think it looks like I used almost the exact same problem in homework. Huh. Or not in homework, in notes. Interesting. All right, moving on. Oh, we're done. Is that the exact same problem? A force of 600? 600. Oh, our theta was 14 degrees in homework instead of 15 degrees. That's a rough change. Anything else? You were supposed to find the weight. That was the exact same. Minus 14 degrees instead of 15 degrees. Okay. Are there any other questions on odds and or evens that you want to receive clarification or explanation for? Yeah, Caleb.
63.
63. I'm just getting the book open. Anybody else? Yeah, Nathan. 91. Nathan and Caleb, 91, 63. Where's my book? There we go. Anybody else?
101.
101. Let me go circle those real fast. What on earth? Yes, please. Okay. Were all of those word problems? Okay. No, just some of them. All right. Let's see what we got. Let's go to chapter. Oh, that's not going to work very well, is it? Right on time. Thanks, buddy.
Yep.
Yeah, struggle, huh? He didn't like me writing on top of it. Who the ambiguous they is, I have no idea. Alright, let's try again. Take 2. Okay. Come on. There we go. There we go. The next page, isn't it? '91 wasn't. Oh. Come on. Anybody else loving technology? Ooh, is that it? Okay, what's our first question? 63. At least I can see that one right now. Okay.
It's so weird.
I'm trying so hard. Too far. Too close. A little bit too close. Maybe moving. Okay, so magnitude, direction, angle of the vector. Kiddos, what were you supposed to remember for number 63? Whenever they say this and this. Yeah, magnitude is distance formula, and distance formula meaning a squared plus b squared. So we could go ahead and just use those components. It's in linear combination form, but they're still components. We could just do 6 squared is 36 plus negative 6 squared is also 36, and magnitude would have been the result of that, which would have been square root of 72. 4 goes into 72, right? Actually, 16 goes into 72. Is it 4 root 2? No. 4 root 6. There we go. No, that's not 6. Is 16 not go to 72? 2 times? Oh, 6 root 2. That makes no sense. I was having too much fun. Yeah, you're right.
4 and 18.
36 goes into 72. Let me write the 72 real fast. I was doing too much mental math.
I'm really confused.
36 goes in 2 times, which means 6 root 2. 6 rod 2. But how do I find the angle? Sorry, we're doing 63. Ignore everything else. That's magnitude. Square root of a squared plus b squared. Hey, good formula for your card on Friday. But how do we find theta? I guess you could. I was just thinking opposite over adjacent and just use, yeah. Can we just use the formula from our notes? Tangent inverse of b over a, so negative 6 over 6. Now I know some of you guys would go to your calculator. That's not totally bad, but tangent inverse of negative 1, isn't that a 45-degree angle? In what quadrant? Oh, I don't know. Well, wait. If we graph negative 6, 6, what quadrant does that put us in?
2 or
Negative 6. 6. Oh, wait, it's positive 6, negative 6. So it would be either 2 or 4, but because of this positive 6, negative 6, I'm going to go positive 6, negative 6. Here's my vector. I'm in quadrant 4, so which 45 do I want? Negative pi over 4, negative 45, however you want to write it. That would be my direction. So you do use tangent inverse. That's all well and good, but you also need to think about the picture. Could have also gone the positive way, which would have been 7 pi over 4, or 315 degrees. Okay, it's number 63. Let's see if this will randomly decide to work now, because I want to go to the next page to see the other 91 and 91. Please, 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 please. That's helpful. Doesn't like this homework at all, does it? All right, take 2. Let's see if we can try it one more time. It's probably like take 4 or 5. they're just blank. How does that work?
Maybe someone deleted them.
Someone deleted them, they just said we don't like those pages. Alright, we'll try one more time. If this doesn't work, I'll go ahead and try to get pictures for you guys tomorrow so we can peek at it. I apologize. Sometimes technology just hates us and I don't know why. Maybe?
You're on the wrong section.
I know, I'm trying to go back to.
And I see it in 6 points.
Why?
Huh?
I don't understand. Alright, we'll just figure that out later. Sorry guys. My kiddos with questions, remind me tomorrow. 91 and 101. We still need to go over 91 and 101. Alright kiddos, 6-4. If you guys notice, I know we still have to finish this section, but oh, look at that homework.
That looks pretty.
How hard's
Everybody
the
a fan of that?
Yes.
Maybe I want a picture of it quick before I take it away.
Darn it, I thought she was gonna let us go down.
Anybody want to write it down real fast?
Yes. Yes.
You want to write it down? It's page 437. 2, 4, 9, 12.
Bless you.
You guys got it on them?
No.
2, 4, 9,
Yeah, I know.
12.
Look, there's the answer.
I know. I'm trying to let people see it in the back. My little cheaters.
Come on.
12, 19,
Wait, let me take that picture.
65, 75. Alright, he's done.
No!
Oh. Ricky, you can take a picture for the next 2 seconds.
Yeah, I know.
Alright, here we go. Let's get back to section 6.4. Our goal is to finish that and start 6.5 because 6.4 is an easy one. We left off here yesterday, and I think I had you put your pencil. Nah, I bet you did that all on your own. Here we go. Get whatever you did not get yesterday. Here we go. While you guys do that, let me take a roll. Orthogonal vectors. Did HGTV ever load today? I checked it like 10 times.
We didn't watch it. Oh, yeah, we did. I need to know. Wait, isn't 2-6?
I don't think it loaded. I heard something about like Valentine's crush sales, something, something, something. Yeah, I never loaded.
Yeah, just that night in the spot.
So expect a bunch of
Yeah, I spotted it. See, you can only talk if you're multitasking.
No, it's
Do you see how much room skips? You can catch up with us.
Even though it's middle school?
On middle school?
It's only middle school?
Anybody else on now? How many pages should they
What,
skip?
4 hoops?
Please say one. 1 and a half. 1 and barely any. Most people are saying 1. I. That's a little extreme. I don't think you need that.
I don't think you can do that. Don't they require you put in your actual name?
Kiddos, you get the example down below. The question was, is it orthogonal, yes or no? So don't just get the notes, get the example. And I didn't answer it yet. Based on what you see on the page, how would you answer it? And I'll ask you in a moment what you got as the answer. And I. Yes, U equals I. I put a little vector arrow above it. Wait, how does I mean 1, 0 again? You guys answered this real quick at the end. I think Nathan answered it.
We were paying attention. We checked on it.
I know, that's why I'm asking again.
It's one eye.
Why does I equal 1, 0?
There's no J.
There's no J. Which means there's no J. Right? Let me zoom out for those of you that were still taking notes. There we go. There's no J, which means 1 horizontally, 0 vertically, finish that dot product, that's practice. Remember yesterday the dot product is first times first plus second times second. First times first plus second times second. Austin, who's just this next to you? No?
Ava.
Mason, anyone usually next to you?
Tyler goes to the room.
Oh, that's right, and then Caleb can do that.
Must be happy about that.
I technically sit there, but
Yeah.
no one can see behind me, so I need to sit back here behind me.
Oral quiz and sandwich. Yeah. She said there's maybe like 3 sets of questions. There's maybe like 3 sets of questions. No, about the.
Alright, Caleb, what's your dot product? -2 plus 0 is? Wait, what's -2 plus 0? -2. The dot product is -2, right, Ricky?
Yeah.
Same coming on back. Does -2 equal 0? Yes or no?
No.
So therefore, are these vectors orthogonal or not? It's as easy as that. Not orthogonal.
So could we just put NO for not orthogonal?
I guess that's a little confusing.
And then NO just equals no, so I mean.
Caleb.
I get it. I'm tracking. Let's focus. Creative. Okay, so not orthogonal. Not orthogonal. The dot product has to be 0 for them to come together at a right angle, and maybe you guys are able to bring some ideas together and say, hey, we like right angles because they form right triangles, which makes the math easier with trigonometry and Pythagorean theorem. If they're not orthogonal, stink. We need law of sines, law of cosines. That's an application of the dot product. Here's one more application. We technically have 2. Another application of the dot product. I'm actually not going to have you guys even worry about the pictures on top. It's a little more advanced than we need to go.
What is it called?
Vector components, but I think let's just go projection. Let's go straight to projection. Sorry, let me zoom in just a little bit. There we go. Projection of U onto V. Projection of U onto V. Vector U. It's in bold. You guys can see it, right?
Mm-hmm.
Projection of vector U onto vector V. So those little vector arrows, vector arrows, vector arrows. I know they're everywhere. I'm sorry. Keep them going. Vectors, 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 vectors. Okay.
Is that squared?
Yes, it is squared. The magnitude squared. So this formula, just to read the formula would be to project U onto V, or you can think of U's force onto V. Be the dot product of U and V, or U dot V, over the magnitude of V squared. That's going to be a constant. It's going to be a scalar, which we can then multiply by vector V. Real quick reminder, even though you guys saw it in homework and we talked about it today, how do we find the magnitude of a vector? It's the distance formula, but if we have components, it's even simpler. It's the A component squared plus the V component squared. Remember, that's all the magnitude is. we square that, we could even just say, hey, the square root goes away. But we can show that math as well. Now, long story short, projection of u onto v. What on earth, how on earth is this applied? You're actually going to see it in an example on the next page. But long story short, the projection. If we're trying to see, and I'm going to go back to the pictures up top. Yeah, we can do that. You don't have to draw this picture though, okay? You don't have to draw this picture. What if there was some sort of box that was way too heavy for you guys to lift? It was way too heavy for you guys to lift, and yet you still needed to move it. A box way too heavy for you guys to lift, but you still needed to move it. Let's say you weren't allowed to get heavy machinery. It wasn't that heavy.
Get a bunch of your friends.
Maybe a bunch of your friends to lift it, but let's say you're still by yourself. Lever and pulley, yes, but what would be something simpler if you just needed to move a little bit?
You take it apart.
How can you put on wheels if you can't lift it?
Flip it.
Flip it?
You take it apart and then put it back together.
Maybe try to do from the behind. But what's another way to do it?
Take it apart and put it back together again. Give
What
up
if
after
you
3 minutes.
tied a rope around it and you tried to drag it?
Kind of like my way.
Okay? Let's see if we can actually find your shoulders
What
wherever
is
it's supposed to
that?
go.
That's a
And you're
really
like,
small
let's go.
part.
Is it like 4 arms?
Okay? Now, I know it's a silly example, but I'm just trying to show you something. If it's too heavy for you to lift, meaning if you were pulling this over your shoulder and you were trying to go, right? And there was like a rope attached to the box, yeah? Where is the box going? Is it going this way?
No.
No, but you're pulling this way. Isn't that the force in this direction? But it's not moving that way. Where is the box moving?
Straight.
This way. Here's an example of how the force that you are putting in, what it results in, how is it is being projected onto the actual object itself. You're pulling this way. That's all well and good. But the box is going this way. So even though you're pulling, we're trying to figure out, would your force be enough, for example, to be able to pull the box? You need to see, okay, as it is projected onto where I want the box to actually be going, what is the overall result of all of my pulling? So the projection basically says there's a vector going, let me get rid of all this messiness. There's a vector going one way, and there's another vector moving a different way, and that's what you see here with here's u going this way, here's v going this way. And we're trying to say, okay, if u is acting on an object and v is the result, then how is this being projected on? That's kind of the idea. Now, I'm not going to make you guys go through all the physics or do the diagrams or any of that craziness. I just want us to see if we can use the formula. If we can apply the math that we've learned about dot product and magnitude. So, we have the problem down below. I actually did not label u and v, I apologize. So let's do u here, and let's do v here. This one's a little bit more complicated because v isn't going straight across, v is going this weird like southeast sort of thing. And if we were trying to figure out graphically, I already just said, oh, don't worry about that. Let's not get too deep into this concept. Let's just see if we can actually use the formula, all right? So the formula is right above. To plug into the formula, we need to first of all find the dot product. What would be, let me just find each of the pieces first, okay? What would be the dot product of u and v? You guys have hopefully been practicing this some. Because 6 times 2 is 12, plus 4 times negative 3 is negative 12, right? Okay, so the dot product is 0. That's one clue. Oh, that's cool. Doesn't that mean they're orthogonal? Huh. Anyway, that's not the problem here. Let's keep going. The magnitude of v is going to equal the square root of, wait, who's v? Oh, this guy, right? So I could say the square root of 2 squared, which is really just 4. Is that okay?
Yeah.
The square root of 2 squared plus the square root of negative 3 squared. I said that wrong. Square root of 2 squared plus negative 3 squared. 4 plus 9 is going to end up being root 13, right?
So 13.
So right now I'm just finding my pieces. I have piece number 1, I have piece number 2, and I think I'm ready to go. So to find the projection of u onto v, I have to do 0 over root 13 times vector v, which is going to be 2, negative 3. But as someone's already pointed out, wait a minute, 0 divided by anybody is.
Isn't it? But it's the magnitude squared. So it's just.
Good call. That's going to change. Maybe something,
I
maybe
mean,
nothing.
it's not gonna change.
Well, I know.
But still good to
It's
be
just a
plugging
point,
in, right?
yeah.
So the square root squared, technically the square root goes away. So it's just going to be 0 over 13. But wait, 0 over anybody is still 0. 0 times 2 negative 3 is 0. So wait, what's the overall effect?
Nothing.
Nothing.
Big
But you're
sense.
pulling so hard.
Hooray for futility.
Yeah, but you're awful.
But it's not helping. You're pulling so hard straight up, and we just said you can't lift it. That's kind of the idea of projection. You're pulling so hard, you can't lift it. It's not going to result in any change. Your projected force on it is not helping it move to the right at all. Okay.
If it's orthogonal, doesn't that mean it's always going to have a projection of 0?
If it's a right angle, yes.
So yeah.
So orthogonal vectors will always have a projection of 0. And that's why if you wanted to move the box, you wouldn't be pulling straight up. You'd be pulling it to the side, right?
Yeah.
Okay. One last application. Let me zoom in, because once again, you need the picture at the top.
Basically, I don't really have a
Caleb, write it down, please. David Austin, let's focus on it. One last application. I don't want you guys to worry about that formula. It's a great formula. It's a good formula. But the overall result of number 1, the first formula, is the easier formula of work equals force times distance. This is a crazy idea. I'll let some physics teacher someday enforce or expand on a little bit more. But the long story short is, even if you are putting a lot of force onto an object, if there is no movement, there is no work being done. Wait, what? Even if you are pushing as hard as you can against a box to try to move it, if you cannot move it, if there is no distance of movement that's resulting, then there is no work being done in the physics definition sense. Which is weird, because obviously we have a very different definition of work. Or maybe not that different if you kind of think about it. Maybe we could say something to the effect of work in the physics sense is productive work. Is work that actually results in something. We're not going to go too crazy on that idea today. I just wanted to introduce it and then just say, okay, so how do we do this whole thing, like finding the work being done on or being done with an object that's moving, an object that's being lifted or pushed or pulled, etc. And how does this apply to vectors? Well, what do we see down there? We see a particle moving from P to Q. To simplify things, there is the picture I wanted you guys to see. But the formula is the most important part, and that's also what you can put on your card for Friday. How do we find the work done in moving a particle from, okay, so from P to Q. Guys, doesn't that mean that P is our initial point? And what's our ending point? Okay. So moving from P to Q. And then it says the force is given by vector V. Now hold on, wait a minute. For this formula up here, don't I want two vectors to do a dot product? I see one vector. I have the force vector. If you want to think of it as V, that's fine. But I have negative 2, 3. Question, what's my distance vector? Exactly. As you guys did in homework for section 6.3, to find the distance vector, we have the force vector over here. To find the distance vector, we just need to go terminal minus initial, like we did in homework for 6.3. Terminal, the horizontal, -3 minus 1, what would be the horizontal component of distance? No. Terminal minus initial, -3 minus 1 would be -4, right? And then terminal minus initial for the vertical component instead, what would be 5 minus 3?
2.
Yeah. Remember, we can always just do terminal minus initial if we have the points. So then all we have to do for work is say, hey, dot product time. This is another very useful application of dot product. So I can just say, hey, it's time to do dot product, which is horizontal times horizontal plus vertical times vertical. You guys fill in. What are the two horizontal pieces of my vectors? -4 and -2. That's the first numbers, right?
2 and 3.
And then my vertical are going to be 2 and 3. All that's left is for me to go ahead and solve.
No.
Nope, because these ones are positive. You see them?
Oh, got it.
There you go. Remember, horizontal with horizontal of one of the other, vertical with vertical of one of the other. So the final work being done would be 14. Now they didn't give us units, so we're not going to worry about pounds or what they're measuring force in, etc. However, we will go ahead and leave it off with 14 and just leave it blank as far as units are concerned. That is our last application of section 6.4. There's a lot more detail that we could have gone into. You guys already wrote down the homework, but let's just go ahead and quickly peek at one more of those work examples. One more of the work examples before we quickly peek into the final section, 6.5. Okay, a tractor holds a log 800 meters. How can we label 800 meters? And this is not logarithm, it's a literal tree trunk log. Cool. Just making sure. What's 800 meters in terms of the formula that we just saw for work?
Length, distance.
Good. Work is force with the dot product of, the way they showed it was PQ. Remember, you can also think of it as force times distance. Okay, so we can say that our distance is 800 meters. What else do we know? The tension in the cable connecting the tractor and the log is approximately. Exactly. You can think of the tension as being the force with which it is pulling. The direction of the force is 35 degrees above the horizontal. Wait, what? They're giving me more information, right? Approximate the work done in pulling the log. Did they give me components for force, or did they give me magnitude and direction for force? Ooh. So this is for my force, this is the magnitude of the force, and this is the direction of the force. How do we get components? Because we want to do a dot product, right guys? So we need a distance vector, and we need a force vector. Why am I leaving so much space on that force vector? What are we going to be plugging in? Yeah, we need to use sines and cosines. You guys remember which one comes first? Magnitude times, is it sine or is it cosine? Good. Magnitude cosine angle to find A. Magnitude sine angle to find B. These are more review formulas from 6.3. That's going to be my force vector. How do I find my distance vector? Here's the ground. We'll just say the log for some reason is like, I don't know, going this way. And we'll say the cable is somehow attached this way up to the tractor who's pulling it. I don't know, whatever. And then there's like, and then there's like the big old. Okay, whatever, he's pulling it, right? How far far does he pull it?
800 meters to the right.
So if it's just 800 meters to the right, then question, kiddos, what would be the horizontal components and the vertical components?
840.
Horizontal is 800 because it's just going to the right 800. Is it going up at all or is it being dragged?
No, it's not going up.
There we go. It's just 800, 0. It's going 800 to the right, which is a positive 800, and it's not going up, so we'll just say 0. Now wait a minute. How do we do work then? Dot product. So work is going to equal horizontal times horizontal, right? Keep helping me out. How do I finish dot product?
0 times
Vertical
15, 600,
times vertical. So ultimately in this section, kiddos, you need to practice the dot product so that you know horizontal times horizontal plus vertical times vertical. And then you have each of your pieces. All you gotta do is add them together. And if I had a calculator or a calculatrice, a calculadora, I would go ahead and punch it in real fast and get you guys an answer. But I think at this point you can plug and chug into your calculator, yeah?
I think, I don't think
So
that's
to
right.
raise it up like even a tiny bit would massively increase the amount of work.
It's not just as simple.
Why?
The answer for the right side is just 0. Yeah.
That was
0
massive.
times
Sine of 35
the number
would be-
times the
I got
number.
like 10 million.
Well, yeah, but like compared to
On the right side?
just that
No, the left side.
like
Okay.
1 meter would.
But 1 meter is
If you got
very
0, if you
big.
got 10 billion, so it's right side, then you got
I
right.
got 10,282,651.
Oh, which one? Did anybody back for Kia?
Yeah.
Cool. What was it one more time?
10,282,651.78.
600 and what, sorry?
51.
Point
78.
780.
Yeah.
Cool.
Wow, Can you not do it right next to the mic?
No, what is
I don't wanna
it?
Without going into physics, this gets a little bit rough. I think it would technically be Newton meters, which I think is joules. Isn't that joules? Are Newton meters joules? Who's in physics?
I think so.
We'll just say Newton meters and forget it.
Nobody that's it.
But physics is an introductory physics. A lot of you guys might have to take a physics class in college for comp sci, for engineering, for anything sciencey, medically, physical therapy. Business? Probably not business.
Probably business, yeah.
All right, cool kids. Section 6.5, calculus for sure, but
Man.
business, but not physics. All right, let's start 6.5. We only have a few minutes, but that's okay because we only need to get a little bit in. I want to get an introduction to 6.5, which seems random and seems totally out there, but it's here because we're doing applications of trig in chapter 6, with law of sines, law of cosines, with vectors, and all kinds of vector math. The last application of trig before we kind of move on past trig in chapter 7. Some of you are like, praise the Lord.
But does it get really bad?
It starts off with substitution and elimination.
Yay!
What does it end with?
Well, maybe. Section 6.5. The last application of trig comes back to complex numbers. The last application of trig comes back to complex numbers. As you guys are writing and setting up, I'm just going to graph that first example so we can see what I mean by real axis and imaginary axis for graphing complex numbers. Complex numbers have a lot of similar formulas to vectors. Hence why this is a good time to talk about them because the formulas hopefully are kind of fresh in your minds. Because complex numbers, like vectors, are built on horizontal and vertical components. The horizontal refers to the real portion of the complex number, and the vertical refers to the imaginary Now, we don't put arrows on complex numbers, they're not headed a certain direction, so that's what's gonna be different with vectors. And we define things a little bit differently, once again, because they aren't vectors, just a lot of the math is the same, because we're still dealing with this right triangle with the horizontal and vertical components. Those components now have different meanings when dealing with a complex number. As you guys are seeing down below, the absolute value of a complex number is what we would also think about as kind of its magnitude. Which, if you go back to Algebra 1 and how you should have learned absolute value refers to the distance between a number and the origin. So if you're on the right, the distance for positive 4 is 4. If you're on the left, the distance is still a positive 4. And that might help you a little bit with absolute value being a magnitude. Kind of makes sense. It's the distance between the origin and a point. That is now off of a horizontal number line, now it's somewhere in space. And actually, this is only 2D space. 3D space would be a bit more exciting. But you guys should recognize this formula of the square root of a squared plus b squared. So absolute value is like magnitude for vectors. It is the distance between the origin and a point. So when we come down here for number 6, the very first step whenever you see a complex number is probably to visualize where it is. And if we have a positive 1, 2, 3, 4, 5, and a negative 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. We can plot that complex number. We know that it should be in the 4th quadrant. Over a little, down a lot. Its absolute value would be as easy as plugging into the formula. No vector arrows on this one. I literally means the imaginary number I. But to solve, we just say, oh, no big deal. We've been doing this for a few sections now. 5 squared plus negative 12 squared, which ends up being the square root of 169, which ends up being 13. So the magnitude, you can think of it as the same thing as the hypotenuse. It's just going to be the length of the number graphed in the real and imaginary axes. Now guys, the application is new, but is the math hard? No, as long as you know your formula. Wait, we're in 6.5, which means don't these formulas get to go on the card as well?
Yay.
Ah, sweet. And totally fine for you guys to label the card as well. Any questions on the example, or can we peek at what's on the next page just for a little bit? Any questions? Okay, let's peek at what's on the next page real quick. We'll stop right here after we get through this quick diagram. Complex numbers in trig form. We've already kind of talked about how a complex number is graphed, and we can see the A and the B. We're going to label the hypotenuse or the magnitude or the absolute value as R. You can think of it R for radius if that helps. You can think of it R for radius. And the nice thing is we can steal those formulas that we saw from vectors and say, you know what? A is going to equal magnitude, which in this case is R. Why are we talking? Cosine of theta. B is equal to magnitude, or we're going to call it R in this application, sine of theta. R is going to equal, as we just talked about, square root of a squared plus b squared. Theta is going to equal tangent inverse of, you guys remember what order? B over A. Just like the vector formulas. What's new, one more time, is the application. Because we're going to take those pieces of information and take what we've seen complex numbers in before, which is standard form, and figure out how to get them in trig form. And then we're going to see tomorrow, why is trig form nice and useful? What can you do with it that you couldn't have done with it? If I can get those corrections in by the end of the day, for favor.
Have a great day, Stuart.
See you guys later.
I will try.
Finish 6-4. Make your formula card, test is coming.